Okay, hi everyone, welcome. Today we're going to have Aurélien Ribes. He's leading the research team Climstat at CNRM in Toulouse, and he's kind enough to talk to us, I guess, in the evening his time. It would be great to hear what you have to say. So thank you.
Okay. Good morning to everyone. So I'm working in the same group as Blanca. I think you had Blanca 2 weeks ago for another talk, maybe more related to machine learning than the one I will present today. And in fact, the idea of giving this seminar was came from discussion I had with Pierre, he was interested in the way we can use part of the framework, statistical framework behind data assimilation, so Kalman filtering, to learn things about climate change and the mixing of observations and climate models. And so this is the subject of today's talks. Okay, so most of this work was done with close colleague Said Kasmi, and there is a series of papers I will present. Okay, so let's go. A bit of context and motivation first. In fact, the context has been evolving quite quickly on this topic. When we start working on that questions, it was before the IPCC AR6, and the context was a bit different. What people were facing at that moment is a new ensemble of climate models, global coupled model CNRS 6. And in this ensemble, one remarkable feature was that there was a number of very high sensitivity models, finally higher than what was found in CNRS 5. And so people were struggling whether they should trust these models or not. At the same time, there was new observations because, between different CMIP exercises, there are a few, typically like 6-8 years. So we had a bit more of observations, and observations were still not warming that much, making high sensitivity models questionable in terms of, again, of accuracy maybe. And also there was a general wish, I would say, to update all results. A typical IPCC report can provide about attribution, the amount of warming that can be found in today's temperature or climate, and many other things about projections. And so there was that key question: can we reconcile high sensitivity models with observations, and can we find a way to combine observations and models to provide the best assessment of both past and future warming? And this is the key topic today. Now, 2023, we are 2 years after the IPCC AR6 was made public and published. And now the context is a bit different. So finally, the IPCC, I will come back to that in the talk, but finally, now the IPCC has decided to use observational constraints, so to use this kind of combination of observations and models to provide an assessment of projections for the 21st century in terms of global mean temperature. But in fact, this, given available literature, this was possible only for global mean temperature, and so regional projections are typically, those provided in the report, are typically unconstrained, and so are not based on the same kind of calculation. And of course, there was a key question whether we can do better on that point and maybe have regional versions of observational constraints. And this is, again, part of the topic today. So the overall question to me is how to combine model simulations or projections and available historical observations to deliver an accurate and consistent assessment of past and future climate. This is really the question I want to discuss. And so we have been working on that for about 3 years now, and I will discuss and maybe browse our statistical method, global application, regional application, and discuss a bit implications and also avenues of that work. Okay, so I start with a few quick presentation of the method. In fact, this is an illustrative example, just to understand how this works. This is a collection of forced responses simulated by 6 models in response to historical forcings and SSP 2 4.5 scenario. So it's an intermediate greenhouse gas emission scenario for the 21st century. Okay, and so this is, I will not explain in detail what filtering is applied to obtain these curves, but it represents an estimate of the forced component of the global mean temperature. And so there are quick cooling sometimes corresponding to large volcanic eruptions, which are simulated by the models in historical simulations. And there is, of course, no volcanoes in the future. So over historical period until 2014, you have the historical forcings. So what really happened in the real world, and after that date, you have a greenhouse gas emission scenario. And in fact, there is a pretty strong range of values in terms of the amount of warming in the 21st century. A bit more than a factor of 2 between the models which warm the less and those which are in the upper bound. And of course, you can take this sample. It's a relatively small sample, but you can still consider this as a sample. Assume, for instance, that the temperature response is more or less Gaussian, which, given the small size of the sample, is not a big issue. And then you get a mean and a confidence range on this the expected warming value. And now you can put on this graph what are the actual observations of global mean temperature over the same period of time. And I forgot to say that, okay, I'm using a reference period here, which is the same as in the IPCC, which is the first 50 years of this period of time. So the second half of the 19th century. So we put the observations. These are yearly value for the global mean temperature. And clearly, it seems that some of the pathways or trajectories simulated by the models are off the cloud of points given by observations. For instance, there are a few estimations below, which seem to be far too cold compared to observations, and maybe at least one above, which is also pretty much too warm, close to +2 degrees of warming in 2020, which is not what we find in the observations. And so the key idea of what we are doing is, can we basically consider that this sample of responses is in an a priori in the Bayesian framework, and compute the posterior of what is possible, both, I mean, especially in the future, given what we have already observed. And if we do that, and I will explain in terms of equations how this works, we obtain this kind of reduced confidence range for the future warming. Okay, but the key idea is to compute which pathways are consistent in terms of temperature, are consistent with available observations. Now I try to put this all into equations. And what we do is, in fact, pretty simple to summarize. So we take a vector, which is a time series. This is the forced response between, so the all here denotes the fact that this is the all forcing response. And you could do the same for specific subsets of forcings, if you will. I take the time series for this quantity. It's a 250 year vector. So this is the vector I am interested in. I want to estimate x, and I write the observations as y, and I have observations available. So at the time we made the study, it was until 2019. Then we assume that we have a prior information for what is the forced response of the system, and it comes from the available sample of climate models. And we assume this follows a Gaussian distribution. So you have a mean and a covariance matrix. It's a big covariance matrix because it's 250 times 250, so pretty big. Not big for people working in data assimilation, but still a bit. And there is an observation equation describing how observations are made on this state vector x. And you need an operator for observation h, which is here. It is very, very simple because everything is global mean temperature. So you just, what you say here is just that the observation, for instance, in year 2000 is exactly the x at in year 2000 plus some noise, epsilon. Okay, so h is just a way to extract the appropriate year in x to make it correspond to what is in y. Only 1 and 0 in this matrix H in this very simple case. And then you have this equation, and so you can so there are a few uncertainty in y. There are essentially two sources of uncertainty in y. The first one is, of course, internal variability, because what you have in observation is not just the forced response. X is the forced response only. So you have internal variability, and there is another source for uncertainty, which is measurement uncertainty. So basically the fact that we don't know exactly the global mean temperature. There are assumptions and uncertainty related to reconstruction, and that is true today and also over the history. Now, when you have settled these two equations, it's pretty easy because everyone is Gaussian, and so you can derive a posterior of x given y, and that's exactly what we are interested in observational constraints. So now, if you take a bit of perspective on these equations, in fact, you can identify everything that is used in two other fields of applied mathematics, I would say. The first one is kriging. So this is exactly like kriging. And the other one is Kalman filtering. And in fact, because we are using here a set, a sample of models, it's kind of ensemble Kalman filtering, but we focus only on the climatic response, so the forced response, and everything else is treated as a noise, which of course is a kind of application that is pretty different from what is done in numerical weather forecasting. And so you have the same 4 key inputs as in usual Kalman filtering. So you have observations, you have an estimate of so this will be called the analysis, I think, by data assimilation people, an estimation of the state of x without any other source of information. And you have 2 key uncertainties. The first one is covariance matrices describing this uncertainty. The first one is a model error. Again, that's the way people in data assimilation call it. And observational error, again, described by this matrix. So and everything, the results will directly depend on how you can estimate these matrices. So estimating these matrices is in fact part of the issue. Okay, I forgot to say that if someone has question about this, what I am saying, you can interrupt me anytime. Better to ask. Okay, so the first thing we have done with that methodology is to test it in a perfect model framework. So we take basically a collection of historical and scenario simulation by various semi-6 models, and we try to apply this technique to predict the amount of warming in the future only based on observations of global mean temperature in the model up to the year 2020, basically. So pretty much the same kind of configuration than what we have to do with the real data.
Well, I can do it. That's not that.
Sorry, this was a question? No. Okay. So the ping. So this is a collection of RAN. Each value is RAN. You have in pink. You have the what is the prior. So the information on future warming just based on the prior. The prior here is made with all other models than the one used for the test. And the red bars indicate the posterior confidence interval, and the black dot is the true value of the model. So this is, for instance, I will take this one. There are a lot of run for this one. This is Canny SM5 because there's a bit large ensemble, so we have a lot of run. I take the first one. We have all these Canny SM5 simulations, and so they gave us an estimate on what is the true warming at the end of the 21st century, which is the back point, and it's the same for all runs because they are all simulating the same, on average, the same forced response. And of course, we want the red bar to be close to cover the true value, which is the black one. And so we use this kind of validation methodology to estimate the coverage probability. So the coverage probability is, in fact, when you calculate, for instance, a 90% confidence interval, which is the case here, you expect the true value to fall within the confidence interval about 90% of time. And so you need to check whether you find this 90% probability to be correct in practice. And that's more or less the case here because depending how you weight models and runs, we are about at 90% for the coverage probability. So this is the kind of perfect model validation of the technology. Okay, now I come to the real application to global mean temperature warming. This is kind of the key figure. So this was described in a paper in Science Advances in 2021, and this was made calculation prior to the IPCC AR6. I have highlighted three key scenarios here: SSP1 2.6, SSP2 4.5, and SSP5 8.5. And the general the key points here are the fact that first, and it was in fact a surprise, we reduce uncertainty ranges pretty strongly. In fact, even at the end of the 21st century, the narrowing of uncertainty is close to 50%, and this is a lot, and we clearly did not expect that a high value. Of course, uncertainty is even more reduced over the historical period because the available observations provide even more accurate information over that period of time. But still, you have this consistent picture of past and future change, which is perfectly consistent at any time, and that's a nice property of the method. Another important result was the fact that both the upper end and the lower end of the range were affected by the constraint. Previous studies, in fact, mainly reported the fact that given the relatively limited or weak warming over the last decades, essentially only the high sensitivity pathways were rejected by any observational constraints. And we also find in this case that there are a few models which in fact do not warm enough, and they probably still do not warm enough at the end of the 21st century. So we are also revising upward the lower end of these ranges, which was new. And another advantage here of the technique is the fact that when we do this calculation, we use the entire observational record. There is no empirical choice about how to select maybe the last 40 years for the trend, and this trend can provide some information, or another period of time, or whether we have to project the observation on a linear trend or another temporal shape. No, you just take the entire record and apply the method without having to care for other things than just estimating the covariance matrices I mentioned before. Okay, and so these results were considered by the IPCC AR6. I will speak more about that later. Now, another thing you can do, I did not provide detail on how you have to adapt the method the equations to make this sort of assessment. But you can also use the same technique to provide revised estimates of attributable warming, what the DNA community has been calling attributable warming, which is in fact the warming related to each, to several subsets of external forcings individually. So this is, in fact, this is this type of result. So again, you have 2 bars for each subset. You have 1 gray bar, which is the unconstrained CMIP6 results, and the black bar, which is the same estimate after considering observations. And so this is a constrained value. You can see that, okay, the warming induced by the natural forcing is very, very small. The value induced by all forcing is exactly consistent with what was shown here. So it's about the same thing, but just focused in 2020. And then you can reconstruct the impact of human influence as a whole, or you can also make the distinction between greenhouse gas and other anthropogenic influences dominated by anthropogenic aerosols. And so, of course, you find a result which is pretty well known since at least the R5 and maybe even before, the fact that there is part of the greenhouse gas warming which is offset by the cooling induced by aerosols and all other anthropogenic forcings taken together. Okay, and in that way you have an estimate of the warming to date. It was a bit above 1.2 degrees in 2020 at the time we made this study. And in fact, because you have time series, and you can see here you have smooth time series, so it's pretty also suitable to estimate the warming rate. And you can specifically estimate the human-induced warming rate, which is 0.23 degrees Celsius by decade over the last decade. And this was again considered by IPCC AR6. Okay, so implication of this work were that, I mean, practically for the AR6 were that the AR6 for the first time considered observational constraint to assess the amount of warming over the 21st century. And this was a kind of breaking point if you compare to previous assessment report, because until now this was not the case. And so previous IPCC report only considered raw, unconstrained CMIP model results. And so here is the figure 4.11 from the AR6. There were 3 studies doing more or less the same type of calculations that I shown before. So Ribes is one of the 3 in violet. And these are the unconstrained ranges for different scenarios at the end of the 21st century. And these are the constrained ranges for the same scenario. And the AR6 also considered emulators, which are in fact very simple climate model, only usually EBMs, so energy balance models, 2 boxes EBMs usually. And this, so because these tools are very, practical, because very cheap, so you can make lots of calculations with many scenarios, which you cannot run with full complexity CMIP models. So that's why they have been pretty much used and considered in the AR6. And in fact, the result provided by the 3 observational constraint methods and the very simple climate models were pretty much consistent. And so finally, the assessment of GSAT warming was based on a combination of all of these sources. Okay. Oops. And then a little after, there was this paper by Ziki Hausfather in Nature, speaking about the hot model problem. And so this paper was essentially explaining that, okay, we have the problem, and if you come back here, you look at the upper bound of the ranges, there is one clear problem in that there is a collection of high sensitivity models in CMIP6, which simulate a high amount of warming for any scenario here, which doesn't seem to be consistent with observations, and which are basically removed or excluded by observational constraint here. Okay, these high values are rejected. And so this should be taken into account. So this is the thesis developed by these people, is that this should be accounted for in any climate impact study, because considering the raw CMIP6 ensemble, there is a risk to overestimate warming and all associated impacts. And so they were suggesting to simply remove hot models from this sample. And of course, there have been pretty much debate within the community whether this is a good idea or not. And our response maybe is that this is not necessarily the best practice, because probably you can find other ways to provide regional information, including the observational constraints. And that's the topic of the new topic now. So I will for this. So this is a different work done. Published last year, 2022. 2 papers describing this, and to explain how we do this, I will focus on an example, one of the study, which was looking specifically at the temperature over France. So okay, France is a small domain. Probably not representative of what is happening in other places, but it's an illustrative example here. And in fact, so in terms of equations, so the method first, in fact, you are just doing the same thing, but you're just considering a bit longer vectors. So this is the time series I had before, 250 years, and this is the global mean temperature. And in fact, what you do is very simple. You just add another time series, same length, 20, 50 years again, but this is a regional temperature. This is a regional response to external forcings. And again, you have 2 types of observations. You have the global mean temperature observations, and you have the regional observations. And there might be some level of some amount of statistical dependencies between these 2 things, which you need to take into account. Now, when you do that, there are at least 2 ways you can think about to implement an observational constraint. The first is just to consider the regional implication of the global mean temperature constraint. So basically, you will constrain this large vector, but just considering global mean temperature observations. And the other step is whether or not regional observation provide useful additional value over the global observation. And that's the topic we have been discussing. The results suggest effectively there is some added values in considering regional observations. Okay, so this is the example. This is a time series of mean temperature over mainland France. So you have one point here for one point is 1 year from 1900 to 2020. 2020 was the record high year in France at that time, and so you can compare this observed time series with various ways of applying the observational constraint. The first thing to begin with is you can run basic smoothing, and if you do that spline smoothing here just without considering models, you get an estimate of the warming in 2020, which is close to +2 degrees. So much higher than the global mean temperature. Now, if you look at the CMIP6 models, multimodal mean, no treatment here. You have this gray line. And this is, in fact, is the mean including the hot models. So even if you incorporate very high sensitivity models, you still feel like over the last 3 decades, maybe almost all years are hotter than what they should have been on average, given the forced responses estimated by this gray line. And so maybe there is not enough warming in this gray line. Now you can implement first the constraint, observational constraint by global mean temperature only. This is a gray line. And when you do that, in fact, as I have shown before, you are essentially rejecting the high sensitivity models. And so you are revising downward the amount of warming over the recent period and also in the future, which is not shown here, but I can say. And in that case, it's then pretty attractive to consider the regional observations. You can either consider only regional observations in the constraint, which is the blue line here. So the fit with the black points is pretty good because there is no other source of observations used in this calculation. And if you combine the two sources, so the global and the regional, you have this kind of red estimate, which is in between blue and green. And you have also a confidence range around this value, saying that basically you estimate the amount of warming between what gives the multimodal mean and the constraint with only regional observations. Perfect model analysis in that case suggests that there is some added values considering the two sources of information, and that's what we will use in the following. And so this is the same picture, but for the future warming, and you can see that in fact it has applying this technique for the future warming over France was pretty important, because we find that finally, despite low sensitivity at the global scale, we find a pretty high sensitivity regionally, and we revise the amount of warming expected in coming decades upward. Again, we find a very substantial reduction of the uncertainty, up to 40 to 50%, even at the end of the 21st century, which is again a very high amount of reduction, especially considering you are at the regional scale. And so, in fact, there is a competing effect in this, at least in this region, between the global observations and the regional observations, and arguably accounting for the two is effective. So the final conclusion with respect to the hot model problem is that in that particular case, hot models are very useful, and in fact they can be useful at least for some specific regions, because observations seems to agree more with these hot models over that region, even if it is not the case globally. Okay, so the global perspective was provided by Kasmi and Ribes in Science Advances again. We try to replicate this kind of analysis for any single location on Earth. So this is just an advertisement of this study. What happens for a few well-known cities, and you can see that the amount of revision downward, for instance, or upward in some case, varies depending on the location, and so the regional observations. And another thing you do in that case is that in fact you are revising and in fact constraining based on observations the pattern of warming. And so this is an illustration of that. This is the pattern of warming at +2 degree global warming level, published in IPCC AR6. I mean, maybe not exactly the same, because I'm not sure we are using the same models, but doesn't matter really. We have shown that if you constrain by global mean temperature observations, you are already changing this pattern a bit. Okay, of course, the large scale, the big picture remains the same. You still have continents warming more than ocean. The Arctic is warming the most, etc. But locally there are some differences. And when you incorporate local observation, you also revise a bit this spatial pattern. And below are the how much you change locally the values. In all cases, this is at +2 degrees global warming. So in fact, we are now at the point where probably observations can be used also to constrain patterns of warming. Quick slide. This is the last one discussion. So our key results, in fact, are, I mean, the first one to me is really introducing this new statistical technique. I think the analogy with Kalman filtering is very interesting because, you know, data assimilation and using this type of statistics for a long time, and in fact there is probably a lot to learn with people involved in that area on how to extend application of that technique and improve the method itself using what they have been doing in data assimilation. So that's the first result, maybe. Other key result, more focused on the application, are that observational constraints now seem pretty effective for constraining temperature changes, both globally and regionally. And there are, in fact, substantial implications for that result. In particular, the fact that we can reduce uncertainty is important for impact, adaptation, and other policies. There is a wide range of applications. So I have shown only temperature here, but we already have started working on other variables. In fact, as soon as the signal to noise ratio is pretty good, pretty high, meaning that there is in the observations an information that can be used to learn things about the long-term change, you can apply this technique and get interesting results. So there have been a few attempts already on the water cycle variables, in particular the amount of water vapor in the atmosphere, which is called precipitable water, and the humidity of our continent. And it seems that in these two cases, we learn a few things in implementing this type of constraints. Probably we can do a similar thing for extremes, not done yet, but that's in our scope. And there is also the possibility, which is maybe a bit new, to try to monitor climate change, because we can probably, and that's something we're working on at the moment, try to update this kind of analysis on a regular basis as soon as you have new observations coming each year. You can redo the calculation and have some gain in uncertainty reduction about both the past and the future warming. This can be important, even you know, just the fact that you can assess the amount of today warming to just monitor how Paris Agreement targets, for instance, are becoming closer. There are a few issues too. The first one is related to the CMIP ensemble. In fact, CMIP is not so perfect. It's very small. Models are not independent. They are pretty much literature describing this. And the design is very poor in the sense that there is no coordinated effort in CMIP to explore uncertainty. In fact, each modeling center develops its own model and tries to make it the most accurate as possible. And no one is trying to develop a model to explore the low sensitivity or the high sensitivity. So in that case, considering this ensemble as a priori is a pretty big assumption, but probably the only one we can use at the moment, but not that good maybe. And also another source of concern comes from all the pattern effect literature. So the fact that in fact, all climate models, CMIP models, are maybe missing important features of the response to the greenhouse gas forcing, in particular in the Pacific region. But the Pacific is large, and so if we have a prior in which all models are similarly biased, it's not good for Bayesian statistics. Okay, and now there is a new maybe a challenge we are trying to face at the national scale. I'm just quickly mentioning here is the fact that, okay, we were used to provide to a wide range of users information about climate change over France and sometimes at the local scale, using a previous generation of climate models. And in fact, regional climate models, the Cordex, Euro Cordex runs typically. But now we have these observational constraints coming into the game, and they are providing different estimates of the future warming. And so there is a challenge how to reconcile these two sources of data, and how to use maybe model outputs which apparently do not warm enough, and given all the new results we have with observational constraints, that's a typically climate services question, but still an interesting one, I think. And I will stop here. Thank you. I'm happy to respond to questions. I suggest to stop sharing, maybe, and see you all. Okay.
Yeah, maybe questions from postdocs and PhD students first, if anybody has, and I'd like, please raise your hand.
Aurélien, can you hear me?
Yeah.
Okay. Yeah. Thanks for a great talk. This is very informative. I have a couple of questions, but I think I'll just stick to one in the interest of time. Maybe this is something that you explained and I wasn't following very closely. But you know, it's just one of those main results of the first part of your talk where you talked about how the uncertainty ranges were narrowed by, say, 50%.
Yeah.
And I think this is one of the issues you also mentioned at the end about like the whole, like about using you know, correlated ensemble members. So maybe, yeah, so just to phrase my question would be, what is this uncertainty range that is being reduced by 50%? Like mathematically, is this the 1 sigma ensemble spread? Or is this the 2 sigma whatever spread for the quartile range? So just being a little bit concrete about what the uncertainty is, and how does this in principle affect extremes? Because you're only talking about, I mean, this is not something that you've shown, but I'm curious about like if you've played with, you're talking about average temperatures, but what happens in cases of, I don't know, extremes, saying like heat waves and so on.
Yeah, so the ranges I have shown were always 90% confidence range, assuming a Gaussian distribution. So it's more or less a plus minus 2 sigma.
Okay.
I mean, no, it's 90%. It's not 95. Okay, so but a bit less than that. But that's what we do, and this is true for the prior, and this is true for the posterior. I always use this type of calculation. Now, the relationship to extremes, that was the question.
Yeah.
In fact, it is pretty important to constrain the global mean temperature because, you know, almost everything in the system scales with global mean temperature. If you are aware of the pattern scaling literature, and this applies to the pattern, but it applies also to change in a wide range of extremes. And so, for instance, if you look at the AR6 summary for policymakers, you have numbers about how much heat waves will change in probability for a given global warming level. So people now provide the response for a plus 2 degree world, for instance. And if you constrain the global mean temperature, of course, you constrain the timing at which you will face this type of change in extremes.
Right. But I mean, yeah, no, I think this is clear, and I am aware of like the Fisher and Nutti paper and stuff, or the you know, the scaling with the extremes and the Rahmstorff even. But yeah, so the question is, does constraining with observations, I don't know, like, because they're only looking at models, right? And I'm wondering if you've like even played around with some of your experiments where including observations would so you would just say that, like whatever scaling that they have for the mean temperature, you would just use your results and use their scaling relationships and obtain the answer for extremes.
Yeah. So okay, I understand. I think the question, maybe your question is, can we learn more and constrain the response of extreme better, accounting for observations of extremes?
That's right. Yeah, because it's a distribution at the end of the day, and this is where you get both from the ensembles as well as the observations.
And in fact, I have another paper trying to do that. So many people try to model from a statistical point of view the response of extremes using a mean temperature of some sort as a covariate.
Right.
Okay, in GeV models or that sort of thing. And we tried to do that, and in fact, then what we tried to do is apply more or less the same kind of statistical technique. You consider models provided prior, and then you have observations which can be used to estimate the posterior in those type of non-stationary GeV models. So I have another paper which I did not mention here about that, but at that time we were a bit less clear on the concept of observational constraints, and so the paper is not written that way, but the idea is here. And in fact, yeah, you're right. You can do that, and it makes sense. And you at the end you get a more accurate estimate of changes in the distribution of extremes that way. Yeah.
I'll take a look at your paper. Thanks again for a great talk.
Thanks. I see a few hands. I let you manage, Kara. Can I?
I think, Robert, I saw your hand first, if you want to go ahead.
Hi, and thanks for this talk. There are many flaws to the CMIP collection of models. You sort of identified that they're not really an ensemble in any way. They're not that collection of simulations with that collection of models isn't designed to sample uncertainty at all. I'm curious, from the perspective of synthesizing observations and simulations, if you had the choice, what would another collection be that would be best suited or better suited to synthesizing with observations?
It's a good question. In fact, so we were aware of a few papers by Retok Nutit and his group about these issues of models being non-independent in particular. So the models typically share a lot of code, and sometimes even all the atmosphere or the ocean are the same in different models. And so there is a clear non-independence between models. And so we have tried to implement his diagnosis of independence and use it in this technique. And in fact, it makes almost no difference. So it was a bit disappointing for us. So the independence issue alone doesn't affect that much the results. So if I had magic power, what I would do to improve that is probably have a look at perturbed physics ensembles, because at the moment it's probably the only way to really explore uncertainty on a systematic way. But it would mean, I mean, I'm aware that there is some available literature on PPE. People do not often, cannot often reproduce all the range of CMIP's responses. So in fact, you systematically explore uncertainty, but at the same time, at the end of the day, maybe you are missing some type of uncertainty. And of course, a very, very ideal situation would be to have, instead of CMIP models, we could have CMIP PPE, I mean, one PPE for each CMIP model. In that case, we can really work with uncertainty probably a bit better. But this is a considerable effort that maybe not that likely to happen. So I'm afraid we will have to work with semi-pensable or equivalent for a long time again.
Yeah, Ellen, I think you're next.
Yeah, hi, thanks for the talk. I think it's sort of shown by your example comparing France to global, the question of, if you're only using one data set, global surface air temperature, what's the best model for precipitation might be different. What's the best model for France might be different, right? So how, and I think this is sort of what was expressed in that piece about the hot models, like how do we, like, the idea of a climate model is it gives you everything, right? How is it by having multiple constraints, or, and I guess, so anyway, so that's the big picture, but basically, like when you're working on precipitation, are you finding that the same models do well, or are you throwing out different models when you look at precipitation? So yeah, that's
it's, in fact, this technique is not a model weighting schema. So most people have been trying to implement observational constraint using model weighting. And in model weighting, there is ranking of model, and you apply the same ranking for all variables. And in somehow you are giving, really a weight to a given model, and it's always the same. It's not the case here. And so that's part of my hope and my response to that. We probably can adapt to what observations are saying, and it can be, observations can have a different preference for some models for one variable and some others for another variable.
So your idea is that you would like do this kind of thing, like I want to study ocean PCO2, and so I would apply this approach to find the models that are most appropriate for that question, and then I would, if I was interested in ocean circulation, I would, I mean, I guess one of the challenges is that we don't have good data for a lot of things, right? We don't have great data for ocean circulation and its variability. So that's then what's the proxy to make that selection becomes a real question.
So in our case, so what can be done to investigate another variable in that context is just to constrain one variable on which we have observations, and then just use, if you run the method I quickly presented here for the two variables at the same time, then the implication for the other variable you are looking for will be based on statistical dependence. And we know lots of variables are related to the global mean temperature, so you can have useful information sometimes, at least in that context. But clearly, if there is no relationship between global mean temperature and the variable you are interested in, this will not work. And in that case, maybe you can try another observed variable. But yeah, I have no more general response maybe to that.
I guess I also had a question related to the hot models, like the regional, like with France being closer to that. Do you think this points to like a bias in like how the models are tuned, or like a bias in the observations, or like, can you say anything about that? And I guess a different but possibly related question, like, can the method be extended to like directly use spatial information, like rather than just temporal information?
Yeah. So my understanding of what happened over France is that, in fact, models, I mean, the multimodal mean, semi-multimodal mean is probably wrong in terms of the pattern. So there, on average, over the globe, there is a bit too much of warming, but over some specific regions, that's not the case. And so we need to reshape a bit the pattern to become consistent with observations. And that's why the idea of just rejecting hot models, all hot models, without further look, might not be that a good idea. That's basically the point of view here. And you had a second part maybe that I forgot.
Oh, I was wondering if like, well, it seemed like what you were doing was like purely time series. Like, can you also include spatial information?
Yeah, so that's one is very good. in fact, we have started using spatial information that is dimension 2. So look at one, I mean, global and just one specific location. Of course, yeah, the first natural idea you can have is, okay, try dimension n. But there is a big challenge in doing that. So basically, the key issue, in fact, is to estimate the covariance matrices I mentioned. So for the model error, you can still consider the spread of models maybe, but for the observations, you need to have, I mean, the size of the covariance matrix in that case becomes huge. Okay, it's the number of time steps multiplied by the number of points all over the years. So it's very big matrix, and you need to get that matrix more or less correctly estimated. You need to be invertible, and at the moment, I'm not really clear on how to do that. Probably there are a few things to learn from data assimilation people, but it really doesn't seem to be easy, and so we were not that comfortable in going to very large spatial dimension quickly, because we need to be very careful how we estimate that. But that's a line of research we will explore for sure in the next 1 or 2 years. Yeah.
Carol, can I ask a question real quick? So it's just a quick question about the correlation in the prior and the observation. So I wonder, is that considered independent, or like how, I might have missed it, but like, do you consider kind of the autocorrelation, like the year after year, if it's close, it helps constrain the uncertainty? Thanks.
Yes, maybe I can just share the screen again here just to show that. Up. In fact, it's that place maybe. You have this. I mean, yeah, this Y vector observations, and so the noise here, as I said, includes in particular internal variability, and here it is a vector. So epsilon is the same size as Y. It's a full time series of observed values, and you are considering the full covariance matrix of that guy, and it includes all the autocorrelation, temporal autocorrelation. So you have all the autocorrelation function in that matrix sigma ops. So yeah, we account for that, and the implication is we need to have a statistical model to describe the entire autocorrelation function. So what we have done here was a bit new to do so, a bit new too, I would say. We used an addition of 2 different autoregressive processes of order 1, because we find it to be very parsimonious in terms of coefficients. You have only 3 coefficients to reproduce the autocorrelation function. And it was very good fit for most of the pre-industrial control simulations. So these simulations in which you can really have a look at internal variability, assess internal variability. And so we find it was a very effective way, model for internal variability at the global scale. And that's what we have been using to estimating this matrix. But yes, this matrix contains all these estimates.